Good morning, afternoon, or evening to folks tuning in from around the world. As is tradition, why don't you let us know where you're tuning in from? Welcome to the 171st episode of the Qiskit Quantum Seminar. Just a reminder that this seminar takes place every Friday at noon Eastern Time and will be hosted on this Qiskit YouTube channel. You can always subscribe to go back and catch up on anything you missed, but you can only ask questions here, live, now, during the seminar. I'm Derek Wong, a research scientist at IBM Quantum, and I'll be your host today. And of course, there's a lot of care and effort that goes into these seminars, so I'd also like to thank video producer Paul Searle and managing producer Olivia Lanes. Today, we'll be hearing a talk by Tomaž Prosen, who will speak about ergodicity breaking transition in East circuits, from dynamical localization to quantum well resonances. Professor Prosen has been a full professor of theoretical physics at the University of Ljubljana since 2008, where he leads a group on non-equilibrium quantum and statistical physics. He obtained his PhD in 1995 at the same university. His main current research interests are in fundamental problems in dynamical systems, quantum many-body dynamics, quantum chaos, non-equilibrium statistical mechanics, and transport theory. And before we have Professor Prosen take it away, hello to Jorge from Madrid, Muzaffar from Kashmir, India. So take it away. Thanks so much for being here.
Thank you. Thank you. So hello, everyone. I'm happy to have opportunity to give a seminar in this celebrated series. So as you see, the title is a bit long, but I hope I can still kind of make it in a compact story. So I will discuss I would say a minimal model of quantum dynamics, a kind of minimal model of quantum dynamics, which is able to show different types of behavior, different, let's say, different phases of dynamical phases of behavior from what I call dynamical localization, which is a form of, which you may think of as a form of many-body localization, to exponential relaxation, which I will characterize by the concept of Ruelle-Pollicott resonances. So I will be actually, talking about some very old work and some very new work, actually, and there will be even some, maybe the last maybe 20–30% of slides will actually be even unpublished yet. So the main kind of discussion, I mean, the model that I'm discussing has been introduced in this recent PRL with Bruno Bertini and Pavel Kos, which we call the Floquet quantum East model, which I will explain in detail in the following slides. But the concepts of Ruelle resonances, and I think that is something that I would really like to advocate in this seminar, because as some of you may have noted, I mean, this concept has been kind of revived in the literature in the recent months. Actually, there was a very nice paper by Takashi Mori a couple of months ago, and just a few days ago, my colleague Marko Žnidarić also posted a paper on the archive addressing similar concept. And this kind of built on the ideas which are proposed 20 years ago, but mainly we forgot, even I forgot mostly about these ideas. But I mean, in the context of quantum simulations these days, this might have some interest. So I will try to discuss this concept of quantum many-body Ruelle resonance and the model of Floquet quantum East, which I will introduce in the next slides. I will claim is a kind of minimal model, specially suited model to discuss this concept of quantum resonances when you address quantum relaxation. So I will be going from localization, from localized dynamics to exponentially relaxing dynamics, and on the way I'll try to characterize this dynamics with let's say simple concepts. As you see, you will see when I go along. So the model, the general class of models that I'm going to discuss will be what I call East circuits or conditional chiral circuits. I should apologize from the start. I'm not following the traditional quantum information notation. I'm using I'm plotting circuits in such that time goes vertically, not horizontally. So please bear with me for that. So I will consider circuits which you can think of as a kind of a brickwork composed of 2-qubit gates. or 2 qubit gates, but for me, I will consider just qubits. So two qubit gates where the left gate is control and the right gate, so the left qubit is control and the right qubit is has an action of a unitary gate. So so this will be kind of a general kind of structure of everything that I will discuss in today's seminar. So I try to advocate that this type of models can be interesting, have this particular chirality, a strong chirality. So they go, the kind of information only propagates left to right in a sense. And a particular example, particular two-parametric example of this type, people call it quantum East model. And what I will define now will be a Floquet version of that quantum East model, and it's basically a gate which has just two parameters. One is the flip rate A. So we have this Pauli X operator here. So one should look at that conditional gate, where you have a Pauli X operator on the second qubit, which is conditioned. So this P is a projector, which is conditioned with probability, with amplitude A. And then there is an overall phase, which is given by this Trotter time tau. Okay, so there are two parameters. Remember, these are the two parameters. One is the Trotter time, and the other is the flip rate, flip amplitude A. And of course, there is a simple kind of quantum information decomposition of this gate in terms of simple rotations and conditional rotations. Now, you can think of this circuit. I mean, I will always think of this as an infinite system. Well, either being defined on an infinite lattice in 1D, but since it has this kind of strong chirality, you can always think of it as being defined only on a semi-infinite, like on the right semi-infinite half of the lattice. So you can think of this as being applied. So for example, I mean, I'm just plotting here a kind of a space-time fabric of this kind of gate. As you will see, it will also be advantageous to think of this dynamics as a ladder, to have a laddered structure rather than brickwork. So you can imagine that gates kind of run from right to left. So again, time goes bottom up. So what comes right is before, what's coming left. So it's like, wind which blows from the east, right? And it affects qubits, right? And these qubits, imagine, are in the beginning, they're in their ground state, right? So then at some point, there is one qubit in excited state, and then the rest of the infinity of qubits is again in the ground state, right? So now, because of the simple property of this conditional property of this gate, everything that's the infinite series of qubits which is in the ground state will have trivial dynamics, right? So all these guys are in the ground state, and they are keeping themselves in ground state. But then the qubit that's excited remains excited because there is no way to change it, because everything to the left was in the ground state, so that these gates are all trivial then, right? If the guy on the left is in ground state, there's no way to change the action qubit. And so this qubit remains in one state, in the excited state, and then everything to the right of it basically follows this semi-infinite brickwork structure, right? So it has really a well-defined edge, right? This edge basically is a consequence of having a well-defined excitation, right? So then this excitation defines the leftmost qubit, and everything, all the action basically takes place on the right, to the right of this, let's say, excitation qubit. Yeah. So then basically what will follow now will be dynamics defined with respect to this guy, this circuit, and this circuit is applied on a specific initial state. And so this initial state I will denote as a simple bullet, right? So in my diagrammatics, so the ground state. And since again, due to this property of when I apply when I apply this gate to two trivial states, right, to zeros, right, basically things are, vacuum state is invariant, right, with respect to the gate. So I can simplify this circuit, right? I can erase all these guys here, to something that is simply defined, to partition sum, which is defined on this triangular lattice, right? This triangular shaped lattice, right? So this is my fundamental domain, if you want, space-time domain, where I want to understand my state. So basically, I have a trivial state. I apply the dynamics on it, and then I have a state which is highly non-trivial, right, which I would like to understand. Okay, so now this is what I call now a kind of dynamical process, right? It's a kind of quantum dynamical process, and it depends on t. There is only one parameter, which is t. So the number of qubits I need up to time t is exactly t. So everything to the right of t is, again, doesn't take place. It's irrelevant, right? So the only qubits which can get excited are qubits up to t size from the first excited qubit, right? So there's a finite kind of light cone. There's a finite speed of information propagation, right? And up to time t, the only t qubits can get involved into the dynamics. Yeah. Okay, so now this, of course, follows from some previous work, and the previous work which I referred to actually has been, there are two papers which one has to note here. There was a first paper which introduced quantum East model, was the paper by Juan P. Garajan and collaborators in 2015, where they claim that this is kind of a nice model which displays localization without disorder. And the reason why it displays localization comes from glass physics, where the quantum Hamiltonian can be interpreted as a stochastic Hamiltonian, as a generator of stochastic Markov chain. And but there's this flip parameter, which here it's written as e to the minus s. This is exactly my a parameter from the earlier slide. This flip parameter actually provides phase transition. So if only if this s is equal to 0, if the flip parameter is 1, this corresponds to Hermitian Hamiltonian. So this corresponds to quantum Hamiltonian, to Markov chain. Only then it corresponds to Markov chain, so that the sum of probabilities is conserved. And then, of course, but this model, I mean, then people in stochastic community, then they call this activity parameter. And this system displays phase transition with respect to this change of activity parameter. And this change of this phase transition actually corresponds to a localization transition in the, let's say, if you want a ground state in this quantum Hamiltonian, because the ground state corresponds to a steady state. So, right, I mean, of course, remote analogy. I mean, of course, this model from a quantum perspective is a completely new model, but there's been a lot of kind of background in the stochastic community on East models, and you know, Juan P. Garajan and collaborator kind of this idea to quantum community. And then a couple of years later, in collaboration with the group in Munich, they have provided kind of nice tensor network simulations on this quantum East model, showing again a localization transition in a large class of states. This model does not display really MBL type transition, because if you look at the entropy of all eigenstates, you will see that in the so-called localized phase, there are still many eigenstates which have roughly volume law. So this is distribution of entropy with respect to energy for different values of parameter, and this S minus negative corresponds to this parameter A being larger than 1, and this corresponds to delocalized phase. So this entropy is more or less always volume law, but if this S is positive, then this corresponds to localized phase, where this entropy is, well, I mean, it can also be very small, which means there are many states which have small entropy, small entanglement entropy, which means there are many states which are like localized, which have area law. And so, I mean, and then of course you can also look at various other measures like localization length. You can try to fit localization length into the profile. So, but the idea is, okay, this is like a Hamiltonian problem. So we have a lowest energy state, and you find that there are many low energy states, which are almost degenerate, because you can put excitation, remember from previous slide, I mean, you can put excitation qubits anywhere in the lattice, and everything that is excited can all be excited to the right of it. And then, of course, there is kind of degeneracy, soft degeneracy with respect to where you put the excitation qubit. And so you have roughly of the size of the number of qubits, almost degenerate ground states, right? Which have very low entropy. And then you have kind of multiple spiked eigenstates, which have a slightly larger entropy, but still they are almost localized and so on. So this model, yeah, it has lots of, let's say, non-ergodic kind of smelling physics, but of course it's not clearly localized. I mean, one cannot, well, of course, first of all, one cannot do anything rigorous here, anything analytic, but it's very convenient for doing numerical work. And so we picked up from there, and we looked at Trotterization of this model. So the model that I showed in the first slide was basically, can be understood as Trotterization of this quantum East model. So you can just take the Hamiltonian of this slide, you just write it in a, let's say, R notation, where projection operator is given by P, Pauli X is given by X, and the flip parameter e to the minus S is written as A. Okay, And then you can just write a standard Trotterization, right? You take a standard Trotter formula, you take a brickwork, you take a, you decompose the pieces of Hamiltonian into groups of even pairs and odd pairs, which don't commute among themselves. So then you can just write the brickwork version of the Trotter formula, where you write even and odd pieces of the propagator. Even is just the tensor product of two qubit gates, and odd is the one which is shifted by one. So it starts with a single qubit gate, and then it continues as a tensor product. So of course, again, the picture is better than formula. So the brickwork formulation of the problem will be this one, right? And I claim this is basically equivalent. It's really unitarily equivalent to our ladder formulation, which I advocated in the first slide. And I will show you in the next slide really why this is equivalent. So for the rest of my talk, I will really use this ladder formulation of the propagator. So ladder formulation means that I have a non-commutative product of gates starting from the extreme right. So suppose that I have a finite lattice of size L. So I start with a qubit L minus 1L, and then I continue multiplying so that always I overlap for one qubit. So these guys don't commute, but of course, I mean, as you will see, this has some nice, for example, nice property with respect to the brickwork formulation. That is that it has translation invariance by shift by one side, translation invariant by shift by two sides. So in that sense, it's maybe nicer, and okay, depends on your taste whether you prefer this one or that one. And one other thing which I would like to stress here, I mean, if you look at dynamics in this formulation and then you apply it to initial state, which is all ground, all qubit in the zero state, all qubit in the ground state, then as I mentioned earlier already, I mean, this is a stationary state, right? I mean, this state is invariant under action of the gate, which means this gate has a vacuum state. I mean, this gate has a state which it doesn't change, which means that if you take all qubits in this state, it's also invariant. This is something that I would like to think of as a caricature of operator growth, because this is what happens if you look at what Heisenberg dynamics does on Pauli strings, right? A 0, Pauli string would be like identity operator, right? 0, 1 would be X, 1, 0 would be Z, and 1, 1 would be Y, right? So this would be like qubit. I mean, this would be for Heisenberg dynamics, one needs to have q dits with d equal to 4, but this is like a really kind of simplified version or baby version of operator dynamics, if you want. So there is a special state which you may think of as identity operator, and then if you write excitation, which is like a non-trivial operator, this operator starts to grow. Yeah. So the growth is kind of again like what you expect from Lieb-Robinson type of arguments, or just because of the locality structure of the circuit, growth can only happens with a finite speed. Okay, so now let's try to measure some. Let's now to measure some localization or some localizing property of these dynamics as a function of time. And again, I mean, here I really consider an infinite system at finite time. So I really need to say, okay, I have a system which is as large as t, and then it is like it being infinite, right? So I'm really looking at the dynamics of a large enough system, so infinite system at finite time. And I'm thinking of how this dynamic scales with t. Okay, so now this is one kind of simple measure of localization which we proposed in this PRL with Bruno and Pavel, which is simply looking at partial norms. So partial norms means you sum over all the probabilities. So you start from a state which is trivial, right? Imagine, I mean, this was like our initial condition, and then you apply this gate t times. You apply the string of gates. You apply the propagator, one time step propagator. This is a Floquet one time step propagator. You apply t times, and then you measure the probability that the rightmost excitation spread it up to position x. Of course, x cannot be larger than t, but it can be anything smaller than t. So it can be at most t, right? So basically, you have now split the total probability, which is 1, into steps, of how far the rightmost excitation have spread. Yeah. So this is what we call partial norms. Right. And before, I still owe you sorry, I should have showed this before, but I still owe you the simple proof, again, diagrammatic proof, that the ladder propagator is equivalent to the ladder propagator is equivalent to the brickwork. I mean, imagine this is an equivalence of two circuits, right? You can just think of this as two circuits, two unitaries, right? And this is a unitary, which is brickwork, times some unitary. I mean, I should have continued here straight lines, which are trivial, but this is a unitary which gives you the intertwining property between the brickwork and the ladder, right? So this is a unitary, the S is another unitary, and and the equivalence of these two diagrams tell you that this guy is similar to this guy, right? It's unitarily equivalent. So U is equivalent, ladder is equivalent to brickwork. Okay, now I will of course not do any calculations in this talk, but I will still try to show you some nice formulas which have some nice properties. But yeah, for calculations, of course, I will advise you to look at our papers. But there is one very simple calculation that one can do. It's really almost textbook calculation, which is to compute the leading contribution, like leading perturbative contribution to the partial norms. And leading in which order, leading in what parameter? Well, a small parameter, we now take this flip amplitude A. So if you think of this flip amplitude A as a small parameter, because that's actually the action, right? Where action comes, right? Action comes if I just go back to the structure of the gate, right? If A is 0, then no action happens, right? There is no way to change qubits. So A is really the action, right? Is the flip. And so this is a small parameter. If you want to do perturbation theory, we can take it as a small parameter, and then you compute the leading order of perturbative time-dependent perturbative expansion for the partial norm and x of time t. First, we realize that the leading kind of diagram which contributes to this partial norm is the one which flips all the qubits from site 1 to site x. I mean, the minimal order in perturbation theory is the x order, is x order, which flips all the x spins up to from site 1 to site x. All the other terms, all the other amplitudes will have higher orders because they have to flip more spins. Because if you want to flip some spins on the left downwards, right, you need a high order process. So this is the lowest order process, and it turns out that, of course, it's exactly order x, right? Because you flip exactly x spins. And it turns out it is very simple algebraic structure. It has a power law A times tau. I mean, this flip amplitude A always comes multiplied with the Trotter time, right? Because you do it in Floquet dynamics, and the amplitude for each step is proportional to Trotter time. So it is A times tau to the x. And then there is a prefactor, k, and this k, again, remember, this is time-dependent perturbation theory. It's many-body time-dependent perturbation theory. So what you get here is basically time-ordered product. It's a time-ordered correlation function, right? A kind of time-ordered phase correlation function. So which means that it's time-ordered multi-time summation of a phase factor, which takes into account the interaction picture structure of the perturbation theory. I don't want to spend too many words because the next best thing is to try to derive it yourself, because it's very elementary, but the structure of this expression is kind of remarkable, and it's remarkably simple, and it allows us to make some rather interesting conclusions. First, of course, you can sum this up. I mean, this is basically if there was one here instead of this phase, this would be just binomial symbol, right? But it always satisfies the simple recurrence relation. And if Trotter time would be 1, this is recurrence relation for binomials. If Trotter time is not 1, this is what people call Q-binomial coefficient. So it's some deformed version of binomial coefficient when the formation parameter is unimodular, is e to the I tau. So there's lots of results and lots of knowledge about the behavior of these Q-deformed binomials. And and one thing which is particularly useful for us will be that their behavior with respect to rationality or irrationality of tau. So again, let's write our final result now in a compact form. So the leading order asymptotics, small a asymptotics of the partial norms has an exponential, right? Something that has an exponential profile. In particular, if A times tau is smaller than 1, this drops exponentially with x. But then it has a prefactor which is combinatorial. It's combinatorial, and it comes with phases. It comes with interference, which is a key feature of quantum mechanics. And that thing can either grow super exponentially or not grow. And as you will see, it really depends on the commensurability of this deformation parameter. So the commensurability of Trotter time with respect to 2 pi. So there's very nice commensurability transition here, which we can control rigorously, but of course, this is only controlling for leading order perturbation theory. For example, if t is of the form 2 pi c over d, where c and d are two coprime integers, then you could show that this means that q is a root of unity, and then the behavior of q binomial is similar to the behavior of normal binomial coefficient, which is super exponential, which means that if you want to characterize this profile of partial norms, this means that the maximum of the profile drifts ballistically. So which means that the system basically doesn't localize, but it's basically just ballistically spreads inside the lattice. Yeah. So we have a closed form expression for the average x. However, on the other side, when you have an incommensurate Trotter time, which means that it cannot be written as a tau over pi cannot be written as a rational, then you can use a simple result in classical ergodic theory. It's a simple result in dynamical systems or mathematics, if you want, which allows you to show that this binomial coefficient cannot grow. The idea how to show that is to write a logarithm of the square of binomial coefficient as a sum, and this sum basically is okay. You can map this sum to a ergodic process which is called linear shift on a circle. So it's simply a rotation. It's a uniform rotation on a circle. But if rotation on a circle is with incommensurate angle, then you can define the averages, and these averages exist. And the process is ergodic, so the summation, the sum can be written in terms of the distribution. Flat distribution over a circle, right? So you can show that this guy cannot grow, right? So that's really kind of distinct features, right? Commensurate versus incommensurate. You can use that to show that in one case the perturbation theory explodes. In the other case, it's controlled by well, at least leading order perturbation theory is controlled by exponential. Right, and now let's compare this to some numerics. So then we have done some TBD numerics, which in this case can be done extremely easily and extremely efficiently. So it's really that is like a perfect test bed for learning TBD. So you start from a simple state, and you make a matrix product ansatz, and you keep this state within MPS form, and you see that you need very, very moderate entanglement entropies, so the distribution of Schmidt coefficients is extremely sharp, and so that of course all happens for small enough flip parameter A, right? So this is some data shown for A 0.1 or 0.2. Now you see already that even simple-minded DMRG simulation shows a dramatic difference between rational and irrational tau. When tau is irrational, which we usually take tau or pi being the golden mean, in this case, these partial norm profiles really decay exponentially. These different colors of curves correspond to different times, which go from 0 to 120 in the steps of 20, I think. And the bullets corresponds to perturbative results. So this is numerics and leading order perturbation theory. Qualitatively, they agree very well, but quantitatively, point-wise, there is still some discrepancy, which is obviously expected because this is just leading order perturbation theory. And in the inset I show the dynamics of the entanglement entropy for a bipartition cut at x. So you take first x sites and then the rest of L minus x sites. You look at bipartitioning, entanglement entropy of bipartition, how it decays how it increases possibly with time. Here you see that first of all it's very small and there is no systematic dynamics, but it's just some sort of quasi oscillations. Now, if you take, and this is true also for 0.1 and 0.2, but if you take rational tau, if tau is, for example, 2 pi over 3, in this case, you find that, first of all, leading order perturbation theory doesn't capture numerics at all. And also numerics shows a clear ballistic trend. So even though the profile for each particular time seems to be kind of quasi-exponentially decaying, but there is still a ballistic growth of entanglement entropies, and there is also growth of profiles when you increase the time from 20 to 120. Even worse for 0.2, where we could only simulate times up to 60 because TBD doesn't work anymore because of too high entanglement. Okay, now when you go to larger flip parameters, then you find clearly some sort of transition. Now it's very hard, of course, from numerics to establish really where is the transition, but it turns out that A is 1 should be enough to claim that there is ballistic or ergodic dynamics, ballistic transport of partial norms, or kind of ergodic dynamics. And this we can do for exactly on our computer cluster for L equals 36 or 36 qubits. So then we can run dynamics exactly up to 36 time steps. So no approximations. I mean, this is quasi-exact. Okay, now this is of course nice for kind of theoretical investigations, but if one wants to do something more practical, or maybe one wants to address this type of transition on a quantum simulator, then one should probably think of some local observables, right? Something that's much easier to measure. And here I'm showing some experiments, some numerical experiments, on how does this dynamics manifest in a simple local observable, which is like local magnetization at position X, for example. I mean, here I'm looking at local spin polarization at position X, starting from the same initial state, running dynamics for T steps, and then measuring Z at position X. Yeah, and then of course this depends slightly, or that depends. This depends heavily on X. Of course, if you look at polarization of leftmost spin, you see, of course, again clearly that in that. And here I look at again dynamics for incommensurate time. So for the rest of my talk, I will only look at incommensurate times. So where dynamics before was showing this nice transition for small a to large a from localized to ergodic. And I will look at here different times, different flip parameters from 0 to 2.0. You should remember these numerical values for later, because I will use almost exclusively this parameter set when I will characterize ergodic dynamics. Yeah. Now this of course A is still localized. This is somewhere in the middle. And then this is clearly extended or ergodic. And now looking at dynamics of a leftmost qubit, a polarization of leftmost qubit, right, as a function of time. Here I'm comparing two different system size, 24 and 30, just to show that for times, of course, smaller than L, things should exactly match, and even slightly longer than L, because the excitation should come back, right, to disturb the spin at site 1. So basically, you roughly have exact dynamics up to time 2L, and then after 2L, still things get different. Now, if you look at spins more inside the system, like this is the second spin, third spin, and Lth spin, then of course things start to move later. But then, of course, so the finite size effects are larger. Okay, now let me try now to change gears and define something very different. I mean, of course, so far we have just looked at finite systems, unitary dynamics. Now we ask ourselves, I mean, is it possible to define some sort of effective open quantum system which describes this model, better than the unitary model itself? So is there a way, because we know that, we have an infinite system and things run from east to west, but now we want that things, that in kind of excitation which went west never comes back, right? So we want it to be forgotten. So we want somehow to make an absorbing boundary condition. We want to mimic a finite system, an infinite system with a finite system with absorbing boundary. And the way I proposed to do that is to attach to this to finite chain. So you take a finite east chain and then to attach to it a so-called reset quantum channel. So very simple open quantum system, which you can write in this time spring representation like this. So you imagine there is an L plus first qubit, which you put in state 0. Then you tensor product it with a density operator for first L sites. Then you apply a dynamics of for one time step for a system of L plus 1 sites, and then you trace out the L plus first qubit, right? And then again, after that, you imagine that L plus first qubit is again back into the 0, 0 state. So trivial state. So it's reset to 0. Yeah. So now, from now on, of course, this is an open system dynamics. So one should use some sort of characterization of open systems. I mean, we should now think of dynamics of density matrices rather than pure states, right? Because the state of our system becomes a density operator. So we'll now write this into a so-called folded or thermophile double or vectorized picture. So we think of these two gates to be joined together. So this one being folded up. And this is like now going forward and backward in time, right? But just doing in one snapshot. So this is like an operatorial gate, but then again, operatorial gate now is a conditional gate, but now the excitation, the local degree of freedom now becomes no longer a qubit, but it's now a q quad, right? It has 4 states, like 4 Paulis. And now I will denote it by a green bullet, right? Before it was all a pink bullet, now it's a violet bullet if you want. Now it will become a green bullet, green circle. And then I also have to find notation for the reset channel. So a reset channel combined with a local gate for the leftmost qubits. And this I will denote by this blue square. Yeah. So now I will understand now these dynamics, this propagator, this kind of Krauss operator, if you want, for R qubit. I will understand it again as a ladder circuit, now in operatorial space, as a ladder circuit where you first apply this box, which is a reset, and then you apply operatorial gates, which are all unitary, and then at the end you apply this local gate, which is just the small w, right? I mean, you remember there was always this unconditional gate on the leftmost qubit, right? Okay, now this will be now my problem, which I will discuss until the end of this talk. I mean, this system, this model, right? I mean, now I'll try now to understand how much understanding dynamics of this open quantum circuit or Krauss circuit, if you want, how much this teaches us about dynamics of infinite East model, right? And I'm thinking of this about as a kind of a general question, right? I mean, can we somehow truncate an infinite quantum system, unitary quantum system, in an efficient way such that a finite open system will have a lot of features of an infinite unitary system, right? So this is a general idea. Okay, I will just bear with me slightly more, and then I will discuss this idea from a more general perspective. So first of all, of course, what is remarkable about this East model is that this simple reset channel already provides, I mean, is good enough to thermalize the system, to provide, which is slightly non-intuitive, right? Because a reset channel basically tries to polarize the rightmost qubit to the down state, but the fact that the qubit East gate is kind of propagating left to right, this combined together basically allows us to prove that this box applied to a unit state, unit density matrix, keeps unit density matrix. So unit density matrix is a stationary state of this process, right? So it is easy to prove, right? You just connect these two wires, and then you think, you know, from the basic property of the conditional unitary gates, you find that this is basically just, again, full wire. Okay, so now, taking the whole machine, right, you apply this whole machine to a sequence of circuits, that is to a density matrix, which is unitary, sorry, which is infinite temperature, which is unit matrix, then it gives back the unit matrix. Okay, so this means that unit matrix is at least, or infinite temperature state is at least an invariant state. One has to work a bit more to show that this is a unique invariant state, and it's also possible to show that. Okay, now let's now compare our open system, our closed system dynamics, which I showed earlier, with this open system dynamics. So again, I can compute, let's say, and in this particular case, I show the qubit on the third side. I don't know why I decided to do that, but it's a qubit on third side as a function of time. So I mean, polarization of the qubit on third side, measurement, average polarization of qubit on third side as a function of time. And this I compare now with system of size 24, 30, right? You see these full lines. And then I compare with an open system of half the size roughly, right? 12 or 16. So now you can imagine that, you know, in order to preserve complexity, you should take half of the system size, because you can only, in your classical computer, you can only store that many, that large register, right? So if you want to keep the full density matrix, you have to sacrifice half of the qubits. But even so, you get much more accurate description, it seems, right? Because first you have, of course, exact match, but then after a very long time, you see that basically the open system dynamics still shows very nice exponential relaxation, while closed system dynamics already shows these bumps, these revival bumps, which are because you have unitary dynamics, and since the system is finite, you know, information starts to, you know, back react from the right hand, right? So it's it's not really the property of infinite system. It's a finite size effect, right? So this is really, I mean, to demonstrate that this kind of simple idea of putting the sink on the right reduces strongly the finite size effects, right? And yeah, of course, you can do this a bit more systematically. You can look at how it goes, how this this time-dependent local polarization for open now reset chain shows depends on different on this flip parameter A. So this is for A 0.2 to 2.0, and as a function of x as well. So this is for x1 2 3, and this is for x on the right hand, so which is equal to L. Now I can just plot some sort of phase diagram, or if you want, I can understand, for example, I can understand the polarization at the leftmost end of the open chain as a kind of order parameter, and now I can plot this order parameter as a function of the flip parameter A, and I see this kind of nice kind of phase transition diagram, right? Of course, this is very kind of heuristic and empirical, right? I mean, we don't really know what will happen in the large L limit, but you see that going from 12 to 16, things don't change really much. And there should be kind of a sharp transition, looking like sharp transition before, somewhere between 0.6 and 1. Now, this can also be generalized to 2 dimensions. And this is just a quick couple of slides to show that one can define a similar model in 2 plus 1D. For example, one can define now a lattice of qubits, and then you can first take a vertical layer of vertical east gates, and then horizontal east gates, and then you can take a layer of vertical east gates, again going from the edge towards the east. So this is like a northeast circuit, right? It goes, the wind blows from the northeast, right? So first east, then from north, and then in order to get anything non-trivial, you have to also provide some sort of excitement on the lowest left qubit, right? Because if there is no excitation on lower left qubit, then the trivial state will keep trivial, right? I mean, we don't want that the system has a simple invariant state, right? We want that this system produces an interesting state out of simple invariance, out of a vacuum state, right? So this is crucial to kind of kill the stationarity of a vacuum state. Okay, so this is a kind of corner impurity gate, and then just this would be like the full description of the circuit with the resets. Now you can put resets on the left and on the top boundary, of the right and the top boundary, and then you get pictures which look very much like in 1D. So then, as a function of now it's just comparing 2 different values of the flip parameter, you find something that doesn't seem to decay very strongly, or maybe not at all. At least if you look at just the first qubit, right, to something that decays very fast. So yeah, I mean, this is, well, I mean, in 2D, of course, things are kind of very, very much, I mean, you cannot simulate very much for a classical computer, so they have very strong sensitivity to system size. But still, I mean, if you look at how this polarization of edge qubit at maximal simulation time, how does this change as a function of A, you see that's kind of phase transition. Yeah? Okay, now let me just, for the last 15-20 minutes, maybe, let me now try to discuss the, why I'm kind of excited that this may be kind of a further simplification on the concept of real many-body resonances or quantum many-body resonances, which I proposed many years ago. And yeah, there is not much development after these papers, but it seems that maybe now is the right time that we should rethink about these ideas. I mean, there is, of course, I mean, this seminar is much too short to give you a good introduction into the concept of real resonances. The concept itself is kind of a mathematics concept which was developed in the theory of dynamical systems, and it applies to sufficiently chaotic classical dynamical systems, so sufficiently hyperbolic dynamical systems. And there people like Ruelle-Pollicott have proposed this concept, and people found that one can define some sort of transfer operator in the appropriate sense. So you define dynamics in classical phase space on appropriate function basis in a function space, such that the operator becomes subunitary, and its eigenvalues dictate decay of correlations, right? Because you can write correlation functions in terms of iterated operators. Now, back in the day of 2002, I proposed to use some analogous idea to discuss decay of correlations in quantum many-body systems, in particular in quantum spin chains, in particular in Qiskit model. I mean, Qiskit model is maybe the simplest and cleanest model to discuss this problem, let's say, in the bulk. I mean, this is slightly different than what I'm discussing in the East model, so this is just a slight sidetrack. But I mean, in the East model, I would claim it's even simpler because we have an edge. So we look now at localization around the edge. But here is really localization of local translation invariant operators. So the idea is, okay, you take local operators, which are spanned by Pauli strings, which have support R, maximum support R, and then you truncate everything, and then you apply Heisenberg dynamics on these Pauli strings. And then if the support grows beyond R, so in one time step, it only grows to R+2 maximally, and then you truncate, you put to zero, you project out all the operators which are too large, right, which grew up out of the maximal support size. In this way, you define dynamics which is subunitary. Yeah? And if you look at the spectra of these transfer operators, which are unitary Heisenberg dynamics times a projector which kicks out long operators, then you'll get the spectra which have the dominant eigenvalue, which does not really depend on the size of support, but on the maximal length of the operator that you keep, right? So it's something like when you do coarse graining in classical phase space. When you look at chaotic dynamics, basically what you have to do is do coarse graining. You don't care of some smaller scale, which is smallest resolution that you can measure in phase space, and then dynamics becomes effectively dissipative, right? That's how dissipation comes about, right? So, I mean, this is kind of a model for quantum dissipation from the operatorial perspective, right? And it turns out it works very well, and it's something that's very similar to what I'm trying to do now with the East model, right? So there I'm taking out all the operators, all the density operators which grew longer than L. Here I dropped out all the operators which grew larger than R. Yeah, and then this is an picture from the old paper where I compared the correlation function. This is correlation function of the Z magnetization in the Qiskit model. I compared this for a finite system. Again, this is finite system of size 12 and 24 crosses and bullets. But then I compare it with the calculation based on the exact truncated transfer matrix, which is this dash curve. Which agrees very well in the beginning, and then it goes linearly. And then, of course, I can also compare this to the leading eigenvalue. Yeah. So this is very similar, right? But now the question is, can we find an efficient method, or can we have some at least a good empirical understanding of how the structure of these eigenvalues and eigenvectors, as I will show later, I mean, how does it behave? And it's an open question. I mean, if we can describe this object analytically, but at least, I mean, it seems that these are kind of nice objects that can explain ultimate decay of correlations. I mean, I forgot to stress that, but if such real resonances make sense, that's also explained that the large class of correlation functions should decay with the same rate, right? Because any operator which has an overlap with an eigenvector, eigenoperator with this eigenvalue, will decay with the same rate asymptotically, because the rate of decay will only be given by the eigenvalue, and the eigenvector will only contribute to the prefactor. Okay, so now there is a bit, okay, I didn't want to get technical here, but you can just try to be a bit systematic and try to say, okay, now let's take our Krauss operator. Now this is like open system dynamics. Let's now think of it as a Ruelle transfer operator. And let's make a spectral decomposition of it. So then there are these generalized density matrices, right? Rho 0 is the steady state. Rho 0 is trivial, right? And then there are these left and right eigenvectors of this W, right? Right eigenvectors being rho and left eigenvectors being chi. Remember, this is not a normal operator. This is not a normal matrix. So the left and the right eigenvectors are not equal. Also, the spectrum can in general be complex. And what you need to have in order to have a well-defined spectral decomposition, you want to ask for bi-orthogonality of this set, right? These two guys, I mean, defined with respect to Hilbert-Schmidt product, have to be bi-orthogonal. Yeah? And then you can use a canonical basis, and canonical basis should be just a Pauli basis, right? And the Pauli basis should be just 4 to the L strings of Paulis, which I will sometimes code with a simple integer, which is just an integer where its digits are Sx, right? X going from 1 to L. So X is just the position of the digit. The least important digits being to the left, most important digits being to the right. Yeah. So this is the way I will code the components of these density operators. And then you see there is a simple, I'm using this spectral decomposition, then you can write correlation functions. Correlation functions now a simple overlap of the initial state with the right vector times the observable overlap with the so initial state overlap with the left vector, observable overlap with the right vector, times the eigenvalue to the power t, right? So this coefficient is simply the overlap of the two eigenvectors, and then there is the coefficient to power t, the eigenvalue to power t. So now suppose there is a well-defined isolated leading eigenvalue, then this will explain your decay of correlations asymptotically, right? Asymptotic decay of correlations will then be explained by simply the first term, and then will be high order terms, right? And now if this happens, if this, if this explains phenomenology, then I would call this that we have a quantum Ruelle-Pollicott resonance, and the corresponding eigenvector should be called a resonance. And this is now spectra of these open quantum systems with a reset boundary channel on the right end for the East model. These are for two different parameters A, and for two different truncation sizes, 5 and 6. This is something that I can still compute with ease on a classical computer. And you see what is really remarkable is that this leading eigenvalue basically sits at the same spot, independently of how large a system is. So it has a kind of it's frozen when you change the system size. Now, if you look at more systematically how this spectral gap changes with the system size, now I should write here capital L, my system size is capital L. You see that there is very nice freezing, and yeah, if you look at 1/L scaling down to L to infinity, you see that it's basically note that this scale is of course not from 0, but it's amplified scale. So you have a very nice convergence and very nice freezing of the leading eigenvalue. Now, you can also compute some other interesting things. For example, you can characterize these eigenvectors. I mean, there's one thing which I want to stress. Of course, I have no time to explain in detail, but what is remarkable is that these eigenvectors, of course, I want to define these eigenvectors in the limit L to infinity, but there they should not correspond to L2 normalized vectors, right? The coefficients, I mean, these coefficients, I define these coefficients of eigenvectors in the Pauli string S. These coefficients, sum of squares of these coefficients will not be finite. What will be finite will be overlap. But since this corresponds to a subunital eigenvalue, which is inside unit circle, then the sum of squares of elements of rho or chi should not be finite, should diverge. I mean, otherwise the eigenvalue should sit on a unit circle. It's easy to show that. So it's really kind of remarkable that you have these eigenvectors which are no longer, I mean, they are no longer eigenvectors of unitary matrix, so they are not corresponding to some L2 normed wave functions. Okay, so right, and now what is kind of remarkable, but that if you look at partial norms, if you look at partial overlaps, not the norms, but binorms, I would call them binorms. So if you look at, of course, the total UX, I mean, if you define these binorms as a sum over product, inner product of coefficients of the dominant left and right eigenvector for a string of a given size, right? For a string of size x, which means I have a Pauli string which is precisely size x. So my rightmost so this is like Pauli string which is excited at position x, so it means it's not shorter than x. If you sum over all if you sum these overlaps, if you sum this over all these Pauli strings of size x, then of course sum over x should be 1, because this is how it was normalized, right? I mean, the left and the right eigenvector have been normalized to dot product 1, but all these kind of sub dot products, I mean, are also positive, it turns out, and they decay exponentially. So it means that this kind of sum seem to nicely exist in the thermodynamic limit, right? I mean, remember, this is now experimental mathematics. We are not even sure that these things make sense mathematically. So we're trying to kind of slowly build it, right? And for that, we have to increase the system size and check that these things make sense when you take a larger and larger system, right? And it only makes sense if these guys would decay sufficiently fast. And it turns out this is like different system sizes from 16, 15, 14, 13 up to 12, 11. So we see that there is a nice exponential envelope of this partial norm profile. And now if you compare now the data for the observable, right, that is the observable is again the polarization of third qubit as a function of time. If you compare this with 2 to 3 different methods, looking at a full open system, full closed system, then open system dynamics, and then only the leading resonance, this is the full line here, you see that you have a very nice agreement. I mean, the leading resonance, of course, only gives us the long time decay, right? Short time decay, of course, is given by all the spectrum, but still, I mean, if you see that the long time decay is very well captured by the leading resonance. Okay, now, yeah, I'm almost done, but for the end, I would also like to discuss a little bit the structure of the resonance eigenvector. I claim that this resonance eigenvector should be really nice kind of fractals. I mean, so that they should make sense kind of in the bulk, right? I mean, now I'm basically, let's say I'm looking at this Pauli coefficient. Now I will drop the index 1 here. I'm always referring to the leading Royal resonance. So this is the right eigenvector. This is the left eigenvector. This is a component of a Pauli string U plus 4 to the RS, which means I take first U digits, first R digits, which are encoded by U, and then the remaining digits to the right of R encoded by S. So which means this is like a partial trace, right? I take a partial trace with respect to the partial trace, but trace in the operator space, which is not a physically meaningful trace, is just kind of artificial, kind of reduced density supermatrix, if you want, of this defined with respect to these state vectors. Yeah. So I take these state vectors, I trace out the first are Q dits with d equal 4, right? Few Pauli sites. And then I define this kind of density supermatrix, if you want. And I do it for the right and for the left vector. And then I ask whether there's some scale invariance by tracing over the additional side. So I want to know whether there is a kind of nice kind of, I mean, this is something, of course, that had been suggested already 20 years ago in my first paper, but now in this quantum East model, it looks much, much clearer, as you will see in the next slide. So what I will do now, I will just add on additional summation Q dit, right? And I will ask whether by some chance this becomes proportional to itself. So this is like an exact RG, if you want, right? You do an RG, you trace out one more degree of freedom, operatorial degree of freedom, you trace it out. What you might get is something that just the same as before. You see, this is just R plus 1, so you trace out one more, but it can happen that this is just proportional to proportional to itself. So proportional to the sorry, this should be R here. Sorry, this is writing R plus 1. Sorry, this is a mistake. This should be R here. I'm sorry for that, because this should be writing R for R plus 1, and then you write it in terms of RR, but then it should be proportional to itself. Yeah, sorry for that. I mean, and similarly for L. And then you find that there is some non-trivial scaling kind of constants, right, for the left and for the right and for the right and for the left vectors, which are not 1, not neither 4 nor 2, but there are some numbers, right, which some characteristic numbers which characterize this scaling of the leading Ruelle resonance eigenvector. And of course, one might wonder whether this is kind of something that's easily captured by tensor network methods. So one might wonder whether there is a kind of easy entanglement or Schmidt spectrum of this reduced density operator, right? And you can think of this as a reduced density matrix defined with respect to the state, operator state. And the question is, does it have a simple Schmidt spectrum? And the answer is no. The Schmidt spectrum has long tails. I mean, this is just to make sense out of this. So what I plot here is Schmidt spectra of this R sub R divided by this scale factor to the power R. So it doesn't depend on R. And then I look at it for R 8, 10, 8, 9, 10, and the system size is 16. So I'm far away from left and right boundary. I'm looking somewhere in the bulk. I take some almost bipartition, and I look at the Schmidt spectra, and this Schmidt spectra should be proportional, which is the consequence of this scale invariance. But they don't have fast decay. I mean, you see that this is log plot, and they maybe decay as power loss. For the right, a bit slower than for the left eigenvector, but you know, I mean, the Schmidt spectra are quite fat, But on the other hand, if you look at just scaling of these density operators, or now I just look at the diagonal parts of these super density operators, then you find a beautiful scaling, really beautiful scaling. I mean, I was really excited when I saw that. So it's really, you look at these density, super density matrices, if you want. I just now plot diagonal parts of them as a function of diagonal Pollicott. And for different truncation sizes. So when I truncate out 8, 9, and 10 qubits on spins on the left end, and you see that when I divide them by the scale factor, I get curves which basically sit on top of each other, right? So this is, I would say, quite remarkable, right? And it really shows this kind of fractality of the eigenvectors. Even though I have a finite system, when I go to the bulk, these eigenvectors are really kind of self-similar. It can be defined in a self-similar way. Now, if you look at the full density matrices, again, you find this is like looking at system of truncation R 8, 9, and 10. You see that these pictures to the eye are basically identical. Of course, I should have explained the color code, but it doesn't really matter. I mean, you just see, but I mean, just to convince the eye that these kind of pictures are very similar. So I have this kind of nice kind of scaling. Okay, so yeah, for the end, I mean, there was lots of numerics, which is, as I said, I mean, these last couple of slides were not even published yet, but I think it's very strongly motivating that there should be something easy, something simple going on in this model, or at least this model should be easily describable by these concepts. Okay, so yeah, with this I will end my seminar. So yeah, I try to propose systematic approach to long-time dynamics of infinite quantum lattice systems in terms of coarse graining of operators, which are implemented by boundary reset channels, which I would like to understand as an analog of coarse graining in our phase space. And yeah, and then the corresponding transfer operator can display phase transition by closing the gap of this transfer operator. And then when the gap closes, these eigenvectors would correspond to conserved charges. So one can also detect integrability in this way. And then, of course, there is what is left to do, and this is already being discussed in this paper by Takashi Mori that I mentioned. When I have additional symmetries, one can get more interesting scaling of the gaps. For example, 1 over L squared as a signature of diffusion and so on. This has been discussed in the literature already to a large extent, but within this concept of Ruelle resonances, I think it needs to be discussed a bit more carefully. And yeah, there's lots of work to do. Thank you.
Great. Thank you so much, Professor Tomaž Prosen. That was really interesting. Unfortunately, I'm not quite an expert in this field, so apologies in advance if some of my questions are a little naive here, but we do have some from the audience and some of my own. I guess to lead off, what you just talked about here, studying these quantum Ruelle-Pollicott resonances, clearly there is some classical counterpart. I guess what qualitatively different behavior would you expect from the classical to the quantum version that you just presented?
I think that's what is more interesting is the many body versus single body, not so much about quantum versus classical, because we can also define very similar transfer matrices for classical many body lattice systems like cellular automata. Actually, we are basically working on a project which is exactly that. So we try to define this for a class of classical cellular automata, and the behavior of this concepts is very similar than for quantum spin chains. So I think one can find very much analogous behavior for a cellular automata, interacting cellular automata, than chaotic quantum spin chains. Now, maybe then of course when you look at cellular automata, you don't have you cannot tune parameters, right? Because cellular automata should be deterministic. So you cannot tune continuous parameters, so you cannot see transitions from localized from let's say quasi-integrable to chaotic like you can in quantum systems. So that's much more interesting in quantum systems. Now, if you ask the question about classical, what is known in classical mathematics literature, that's mainly what physicists would call single particle problems. So it's like billiards or motion on a negative, constant negative surface manifolds and stuff like that. For that, analogy is very vague, of course. I mean, that's just, yeah, as I tried to
Mhm.
explain
Okay.
in the beginning.
Thank you. We have a question from an audience member, Shashi Kumar, and it's this, and then I'll generalize a little bit. Is the unitary model of computation a must for dynamical localization? Wondering if it also applies to measurement-based quantum computers, such as the one that Xanadu uses. And I guess I have a more general question, which is that I'm trying to develop this more intuitive understanding for why these reset operations like introduce fundamentally some sort of like interesting complexity into this system. Um, because these operations could also like there is this kind of continuous transition from like a purely unitary to like this measurement-based type system. So yeah, sorry if that's a little bit vague, but if you just generally speak to the importance of these resets in your system that you're studying here.
I think the resets only work because I have this feature of the East dynamics, which is conditional on the left qubit. Um, Otherwise, a reset would not have a trivial steady state. We basically have a steady state, which is, well, I mean, depending on dynamics, but will not be infinite temperature steady state. And in order to define this concept, I need to have a trivial steady state. I need to have a trivial. So the infinite temperature state should be invariant under dynamics. So for that, I would have to define a different channel. I mean, for let's say one can look at, I don't know, some sort of Heisenberg type models or even Ising type models,
Yeah.
Floquet Ising models or Kicked Ising models, again on the edge and then with the boundary. But for that, one would have to define the kind of dephasing channel, not the depolarizing channel, rather than reset, because one needs to have a trivial steady state.
Let's see. And then relatedly, there's a reset at the end of the day is a measurement followed by this conditional X gate, right? That forces you into your zero state no matter what you measure at the end of the day. And so you could generalize this idea to doing a measurement followed by any gate. And I wonder if this is like an interesting axis to explore in this class of systems, not just resetting to a zero state, but other
Yeah.
gates follow. And what does that create in your system that you're studying?
Yeah, I think it is. But I try to have something which is conceptually as simple as it can be. I mean, like, yeah, at least for what I wanted, right? I mean, this reset does the job, but of course you can explore the much more rich class of open processes at the end of the system. But what I really wanted is like a truncation, right? I wanted to have a truncation so that when operator grows too long, I just cut it out. Yeah, and reset does the job. Floquet East plus reset do the job. And I want to have, I mean, maybe that's something which is quite interesting, even though I don't understand it yet, is if I try to compare this to what I did in this paper in 2002, where I just look at long operators in translation invariant sums of long operators, and I cut them out when they grow longer than R. And I tried to understand this as a quantum channel. So I asked myself whether this is a quantum channel, and I expect it to be a quantum channel because it's morally something very similar to what I'm doing here. Here I'm just looking at operators which are glued at the left boundary, and when they grow too far, I cut them out. This boundary problem is really a quantum channel, and the bulk problem with translation invariance seems to be a positive map, but not completely positive. So it's not a quantum channel. It's not something that you can implement using toolbox of open quantum systems. I mean, like this canonical measurement processes. So, I mean, yeah, this is something. Of course, it's in the air still. I'm not fully understanding yet what I'm saying. Even yeah, it's
Well,
that's why I prefer to really fix now this model, because it seems to be very simple. It seems to be easy to understand, at least definition of it and its mathematical meaning. And
yeah,
maybe we can, at the end of the day, even do some exact or some computational results, which
yeah.
are non-trivial.
Well, really relatedly to my very last question, the obligatory one. Yeah, I know you've worked on these kinds of simulations on actual quantum devices before, not this particular one, but other classes of models. And I guess, are there open questions that you think a quantum simulator would be especially well suited for in this particular model or related ones? Do you think it'd be feasible with current devices? What would be the biggest obstacle in translating it?
I think so. I think this would be quite feasible on the current NISC platforms.
Hmm.
Now the question is, of course, if we can. I mean, we all want to go beyond classical, right? I mean, to do something that's at least maybe on, yeah, as at least quantitatively kind of competitive with what we can simulate on a classical computer. This I'm not so sure, but I still, I mean, this is almost kind of, yeah, optimal for that purpose.
Hmm.
I mean, I thought about this a bit, and I think this kind of dynamics would be, yeah, I think worth to simulate.
Yeah. All right. Well, thank you so much for your time. Thanks for the presentation. And then, of course, thanks to the audience for tuning in today. If you'd like to continue the conversation, you can always hop over to the Qiskit Slack workspace. Please like this video, subscribe to this channel, and we will see you here next week. Thanks, everyone.
Thank you. Bye bye.